afternoon, dear students. In last lecture, we were discussing about the AVL trees and its creation. AVL tree is a balanced tree. We have discussed that whenever there is some kind of sorted data in any ascending or descending order, then a binary search tree is hanging towards a single direction, which loses the benefits of the binary search tree. So we started with the AVL tree, which is a balanced tree, and we discussed that how at every step the tree is balanced by using the AVL property. There were four cases of the rotation, you may remember. The first case was single left rotation, and the second case was single right rotation, and the other two cases were double rotations. First single right rotation and then left rotation, and vice versa for the fourth case. So we detailed discussed that whenever there is a node which is inserted into a binary search tree, if it affects or it changes the balance vector of a given node in that path starting from that node towards the root node, then we need to perform the rotation. And we have seen that the balance vector should be in the range of 0, 1 and -1. So and the calculation of balance vector was on the formula of height of left subtree minus height of right subtree. So that was about the last lecture, insertion into the AVL trees. We have also used some data and constructed an AVL tree and performed different rotations, single rotations and double rotations. So whenever the balance vector of any node goes beyond 0, -1 or 1, which is 2 or -2, then we identify the node, name it as the alpha, and then we identify which case of rotation is to be applied on the given data set, and then we rotate that node accordingly. We have couple of examples in the previous lectures. I hope you have practiced and you remember those. So today's our topic will be how we can have the deletion in the AVL tree. We have already seen the deletion in binary search trees, in which we saw different cases. For example, if we want to delete the node which is a leaf node, then there was no issue. We simply identify that node and we simply delete that node. And there was a second case of deletion in which we may have a single child of a node which is to be deleted. So in that case, you might remember that we have performed such kind of operations. For example, if this is the case, this is a root node and this is, let's say, the node which is to be deleted, and it may have, let's say, a right child, this one, and this is the target node which needs to be deleted. So what we have done in that case was we bypassed this path and we connected this parent to the child of this one, like this one, and then we removed this node. So that makes the completion of deletion in case where a node has a single child. Another case was in which the node which is to be deleted has two childs. For example, if we look at this one, this is a tree, binary search tree. This is a root node, like this one, and like this, and this one. Okay, so if, for example, the node to be deleted is this one, then we will see it has two childs, and first we need to find its in order successor. So remember, this one node which is to be deleted, and we found or we find the in order successor of this particular node. For example, we say this has another node here and this has another node here. So the in order successor for this particular node will be, we as we discussed before, that move one step right and then repeatedly move towards the left side until we reached at the bottom level, that is the leaf node. So in this case, this particular node, this one, it will be the in order successor for this node. So what we had done is we just copy the contents of this node to this location. Like this one, we copied the contents at this one. For example, if it was the value, some value, let's say x, so the x was copied at this point, and then we now we need to delete this one. So this, we can see that this is a case of a deletion where the leaf node is to be deleted. Like this node has no left or right child, so we simply delete this one. Okay, so in this case, once we delete, we also need to keep in mind that the BST property, the binary search tree property, should not be disturbed. For example, this value should be less than this one, because this is greater and this should be on the right side of the this one. So this these three cases we have already discussed in case of the deletion of in a binary search tree. Now we will look at the AVL tree deletion. The concept will be same, but one thing we need to be in keep in mind, that once we delete a node, we need to check whether the deletion of that particular node, it has caused some rotations. It needs to be performed. For example, the deletion changes the balance factor of the nodes. If it does so, then we need to perform the rotations. We will see in a couple of minutes with the example. So deletion is the inverse of insert. Given a value x and an AVL tree, for example this t, that delete the node containing x and rebalance the tree if necessary. Like we will be given with a tree t, and then we will be given with a node which needs to be deleted. Is, let's say it is the x node. So for example, this one was the x node. Once we delete that x node, then after that we will see that the deletion of this particular node, if it causes the balance factor to be adjusted, then we need to perform the rotations. If not, then no need to perform the rotations. So it turns out that the deletion of a node is considerably more complex than the insert. Sometime it may have the effect on whole tree, and we need to have perform multiple rotations in order to make the tree balanced, or AVL tree. Okay, so insertion in a height balanced tree requires at most one single rotation or one double rotation. We have seen with the examples that once we need to insert a value into the AVL tree, we just insert it according to the formula which we studied, BST formula. For example, if the value is greater than the root node, the new value should be on the should be going towards the right side of the node, and so on, and we insert that value. So that after insertion, we simply check whether the balance factors are out. If yes, then we perform a rotation, and in a single rotation, single or double rotation, means one rotation, only one rotation will be applied. Either it could be a single rotation or it could be a double rotation. So it makes the tree balanced. Okay, we can use the rotations to restore the balance when we do a deletion. For example, a node is deleted, and we can perform the rotation to rebalance the tree if necessary. But sometime, as I discussed, that deletion of one node can result into the performing of multiple rotations in order to make the tree balanced. we may have to do a rotation at every level of the tree, and hence log n rotations in the worst case can be possible. We will see in an example that once we delete a node, that causes the rotation, multiple rotations, for example log n rotations, to balance the entire tree. So that is more complex in worst case of the deletion. Let's say this is the tree. Here is a tree that causes this worst case number of rotations when we delete a at every node in n's left subtree. The left subtree is one shorter than the right subtree. For example, if we look at this particular tree, n is the root node and this is the left subtree of this one, and this is the, for example, right subtree of this node. And now we are interested to delete a node which is a, this one, a, this is here. So at this point of time, currently it is a balanced tree, and we are given with a request to delete this node a, which is a leaf node. So first we need to find the formula, or we need to check how the a will be deleted. For example, if we recall the concept of deletion, then we will see the a is the leaf node. So in this case, a is the leaf node and we can simply delete this a. But it is not that simple as it seems like in BST, binary search tree. The deletion of a affects the balance factors of left subtree of n and the right subtree of n, and which is written here. At every node in n's left subtree, the left subtree is one shorter than the right subtree. For example, once we delete this one, we will see that this C node is now imbalanced. For example, if we look at this one, this scenario, then it is a imbalanced situation. So once we do the balancing of this one, this we can see the case of a single left rotation. So after performing the single left rotation of this particular tree, we will get the tree like this: C here, and D का जो right होगा, it will be E, like this one. Okay, and this will be this connected to this one. So once this has been deleted, this portion, this left subtree of F is now one shorter than the right subtree of this F. So again we need to check and we need to perform some kind of rotation here, and then after rebalancing of this node, the n will be having left subtree which is one less than the right subtree. It means we also need to perform the rotation at level n. So in worst case, it will be performing 1, 2, 3 and 4 rotations to finally balance this tree. So this is the worst case of deletion in AVL tree. We have deleted a single node, but we need to perform 3 to 4 rotations in order to make this tree a balanced tree. But this was not the case in case of simple binary search trees. So this is the complex or more worst case, but simplest cases, sometime deletion will not be making any rotation. Sometime we need to perform 1-2 rotations and the tree will be balanced. But in worst case, worst scenario, the rotation number of rotations to be performed is the log n rotations. Okay. This is the explanation of what we have just discussed. Deleting A, this one, this upsets the balance at C, this one, C, as we discussed, that the balance factor of this C will be now height of left subtree, which is -1, and height of right subtree, which is -1 into 1, this 0 and this is 1. These are the heights. So the height of right subtree of this one is 1. So -1 minus 1 is equal to -2. So balance factor of the C is now -2. when we rotate D up, C down to fix this, like as we just see in the previous example, like this one, this will be rotated like this, A will be deleted. Now the D will be the root node, C will be the left child of the root node, and E will be the right child of the root node, like this one. So this will be fixed like this. The whole of F's left subtree gets shorter now by 1. We fix this by rotating about F to I, F downs, I up, like this one. So now at this point of time, if we look at this node F, this has the balance factor, it must be in -2 or +2, and now we need to perform again a single left rotation, skewing the I nodes and following the same procedure which we done before. So I move up, F down, और जो भी I का left subtree होगा, it will become the right subtree of this F, and whatsoever is the left subtree of F, it should be the right subtree, left subtree of the F as it is. For example, this should look like this. I will be here, let's say this one, and F will be come the left child of this I, like this one, or whatsoever is the left child of the F should be should remain the left child of this F, like this one. D and E, okay, this one. What will be the right child of F will be this left child of I. So G and H, this should be the right subchild of this F, like this one, and I will be K and rest of the tree whatsoever is there. Okay, so making this again, the left portion of N will be one shorter than the right portion. Again we need to perform the final rotation starting from this point. So the whole of F's left subtree gets shorter. We fix this by rotating about F to I, F down, I up, like this one we just see, and this will make the rotation like this one. This could cause imbalance at root node N, like this portion is one less than the this right portion, so the rotations propagated to the root level. So this is what we need to discuss in the deletion of an AVL tree. The worst case, we will need to perform the rotation starting from that node towards the upper or the root node, like this one. Okay, so this is the algorithmic procedure of the deletion in AVL trees. Delete the node as in binary search tree BST. Keeping in mind the principles of the binary search tree, we delete the selected node, traverse up the tree from the deleted node, checking the balance of each node like we did in the previous example, and then making the rotations if necessary. So dear students, we need to have some exercise from you. We need to construct the AVL tree from the following data. Also we need to perform the necessary rotations at every step. For example, these are the values, given values 12, 25, 35, 45 and so on. So we need to perform or we need to insert these values into a empty AVL tree. First 12 will be inserted, then 25, then 35. So 12 this one, और उसका जो right होगा it will be 25, like this one, and then it will be 35. So at 35 we can see that we need to perform a single rotation. Okay, this one, like this. So after this we will perform a single rotation. It is a single left rotation. So after performing this, 25 will be the root node, and then 25 का जो left होगा it will be 12, और इसका जो right होगा it will be 35. Okay, so this is how it works. So all we need to do is create a AVL tree for these values and perform the necessary rotations where we need those one. Now we want to delete the following numbers and also perform the necessary rotations. We once we constructed a tree, we will perform the rotation deletion. First we need to delete the 30, node 30, wherever it will be we will delete that one, and after deleting we will see which rotations are need to be performed, and then we will once done we will perform the deletion of the 60. Okay, so these are the two values to be deleted, and this is basically your assignment. What you need to do is you need to make a video of constructing this AVL tree with these values by performing the necessary rotations, and then once you have make the AVL tree complete AVL tree, then you need to perform the deletion of these two values. First value will be deleted, and after that if deletion of first value requires any rotations, then you need to perform the rotations, and then you will delete the second value and also perform the rotations. So make a video like this one. You can install any software of your choice. I hope you may have installed some already. You can use the Camtasia software which I am using, and you make this video, and you can make your own YouTube channel like I have made it. You upload your assignment, this assignment number 4, to that and share the link with me by email, not on the WhatsApp group but by email. So this assignment is due on this up to this coming Friday. So please carefully make it. First the AVL tree and then the deletion of the two values. So all you need to do is create the AVL tree, perform the necessary rotations where needed, and then delete the two values. So once the video is completed, you make your own YouTube channel, upload that video onto that particular channel and share the link with me by email, not on the WhatsApp group. So this will be cover many things. It will tell you the skill of creating the channel, uploading, creating the video, practice of AVL tree and deletion, and so on. So please submit it by coming Friday. If you have any questions, you can talk to me, or you can have your WhatsApp group. So this attendance for this lecture will be done in the same way on WhatsApp group. You listen this lecture and mark your attendance on the WhatsApp group. Thank you very much, and Allah Hafiz.